Moin, what's up guys? So I had a ridiculously dumb idea and today you get to watch me suffer through it. I decided to electroplate some insanely spiky 3D printed doorknobs and let me tell you, it was an absolute nightmare of trial and error. I'm testing 3 different versions from standard FDM all the way to resin. I also show you exactly how to save your project when your plating refuses to shine and how to give it that flawless nickel finish at the end. Buckle up, it's gonna be a wild one. Let's dive right into it. My goal here was to test out some new smoothing methods and once again show you the differences between the base materials. For my 3 doorknobs I plated 2 FDM prints and 1 resin print. First up I printed several scaled up amulets on my H2S, all of them in ABS with a layer height of around 120 microns. Since having a completely smooth surface is super important for electroplating, I decided to vapor smooth the first ABS print. To do this you just need a large PP box to put the ABS parts in. You've probably seen the setup around. You hang some racks inside, soak them in acetone and seal it up. The acetone basically melts the layer lines smooth and after about 30 minutes in the sealed box with some light convection everything looks super nice. And don't worry, we'll talk about PPE in a minute. The results? You can still see some faint layer lines and we lost a little bit of detail, but overall it turned out pretty neat. I'm completely skipping the sanding and smoothing for the second ABS print. You can really see those pronounced layer lines and I'm just going to brush it with the sealing liquid I've started using on all my FDM prints. Why? Because otherwise the electrolyte almost always leaks back from between the layers later in the process. Here's what that looks like. My theory was that the sealer would actually help level the surface at the same time, kind of like a clear resin coat. I definitely wanted to put that to the test. I let it soak in for about 20 minutes and then left it to cure for a full 24 hours. As a baseline reference, I'm also making a resin print of the head. If you're doing this, here are a few things to keep in mind. Turn on anti-aliasing and blurring, use very fine print settings to minimize any layer lines, place your supports in hidden spots and clean the 3D print thoroughly at the end. When it comes to curing, you can really go all out. Just remember, every single imperfection gets heavily amplified during electroplating. That's why you can always go back in with a small hand sander afterwards to correct any remaining artifacts. It turned out pretty perfect, by the way. A quick word on PPE, wear it. It's not a fashion statement. Lab coat, safety goggles, respirator and gloves. This is what keeps you safe in your shop. Before we can drop a thick layer of metal onto these prints, we have to make them electrically conductive. My go-to is often copper conductive paint, which I lay down nice and even with an airbrush at about 2 bar. I let these dry for a good while to let all the solvents flash off. Let's check out the painted results. The raw 3D print really highlights those layer lines, so that was a massive success. The vapor smoothed one is looking way better with super small walls, but the absolute winner right now is the resin print, which looks flawless with the conductive coat. Honestly, I'm just waiting for something to go wrong at this point. Time for the core process, the electroplating. This right here is the bread and butter of this channel. I've got a bunch of past videos on this and I always try to bring something fresh to the table or improve the workflow every single time. I do this entirely as a solo hobbyist for fun with no paid ad breaks, so if you want to support the channel, a like or a sub goes a really long way. Thank you. Alright, let's get started. What am I using here? An acidic copper electrolyte, this is about a 5-liter bath, and a power supply that can deliver constant current. I'm also testing out a custom built reverse switching circuit, but more on that in a second. To rotate this 3D print in the bath, I'm using my new controller that supports both servos and steppers. And finally, my rotating jig, which is driven by that controller. From the PSU, I connect the positive to the anode in the bath and the negative to the part being plated. That's your standard setup. Now about that reverse plating controller. The basic idea is to temporarily reverse the plating direction at a specific ratio. This periodically breaks down the high spots and generally gives you much more even surface, though at the cost of some detail. This thing sits between the positive terminal and the anode and works using relays. I hook up the Conductive 3D print, drop it into the bath, and from there I don't have much time to waste. I turn on the power supply, set it to 1 amp per square decimeter in constant current mode and fire up the rotation. To get even better results, the bath is also agitated using a magnetic stirrer. After about 20 minutes I pull it out and you can already see a solid closed layer of deposited copper. But this is also where we see the first defects. These little black areas didn't have any conductive paint or just not enough, so no copper could deposit there. Other than that, everything is still looking good, so back into the bath to keep it going. But then things started getting weird. On the areas closest to the anode, the actual spikes of the 3D print, I started getting some slight burning. You can see that pretty clearly here. To fix this, I placed some current robbers around the peaks. These are basically non-touching dummy cathode that weaken the electric field right in front of the spikes. After setting those up, I just let it hang in the bath for 4 solid hours. What can I say? That worked out beautifully. The brightener is really kicking in and the whole part has a gorgeous shine. You can clearly see how the bright highlighting actually amplifies these 3D printing artifacts. There are still a few dull spots, but nothing a little polish can't fix. Great, moving straight on. Next up is the Vapor Smooth 3D print. I actually built a new frame for this one because just look at how thickly the current rubber got plated. All prepped and into the bath it goes. Pulling it out, you can see a few scattered dull spots here as well. Weird. And by the time I got to the third print, the resin one, those dull spots were getting worse and worse and the bath was just plating terribly. I quickly ran a pH test. Coming in at a pH of 1, we're right in the sweet spot, so my second thought was to switch to a larger bath. More distance to the anode, which meant I could push more power. I also thought about increasing the anode surface area, which should always be at least as large as the object you're plating, otherwise you deplete the ions. Spoiler alert, none of that was the actual problem. At this point, I had enough, so I designed a hull cell and 3D printed it out of a PPSCF to properly analyze the electrolyte. But before I show you how that works, just listen to how incredibly cool this material sounds. Alright, I've got these brass plates here and I'm cutting them down to size so they fit perfectly into the hull cell right into the angled slot. If you've never seen one of these before, here's what it does. Because the hull cell has this asymmetrical shape, our brass test plate sits at an angle to the anode. This is essentially a cheat code for electroplating. The current always takes the path of least resistance. So the side of the plate closest to the anode gets blasted with a very high current, while the side furthest away gets almost no current at all. This shape forces the current to distribute unevenly, giving us a complete map of how our electrolyte performs across a huge range of current densities. Next, I'm filling up with the exact electrolyte bath I want to analyze. I connect the wiring just like our regular setup, positive to the anode, negative to our brass plate. To properly simulate the conditions of my main tank, I'm also dropping a magnetic stirrer to keep the fluid agitated. I'm dialing the power supply to exactly 2 amps and we'll let this plate for 10 minutes. Alright, 10 minutes are up, let's look at the result. You can clearly see the different plating zones. Over here on the far left, in the high current field, the copper is totally burned and rough. In the middle it looks great and shiny, but on the far right the deposit gets really dull and matte. But looking closely, there's an issue. This matte area stretches way too far to the left, creeping into our mid-current zone. What does it mean? It tells us that our bath chemistry is out of balance. Specifically, the electrolyte is starving for organic additives. To fix this, I dose some brightener into the bath. Once the chemistry is corrected, we need to find our ideal settings. I printed a standard hull cell scale on a transparent sheet of foil. You just lay it directly over the test plate, align it, and you can simply read the exact perfect current density range in amps per square decimeter. Now I know exactly what number to dial in for the actual parts in the main tank. Alright, before I toss all the doorknobs back into the electrolyte bath, I obviously need to adjust the bath itself. In it goes. Now I'm just going to run a quick round of dummy plating to get it nice and pure. I'll explain how that works another time. And please don't skip this next part. I really want to say a huge thank you to my many channel members and to everyone actually supporting this channel. I truly appreciate it. You guys are amazing. Alright, hit it. I also dropped in an auxiliary anode and changed the rotation direction. This really helps out with the geometry. Now it's just about staying cool and relaxed. Let's pull it out. That is already looking nice. And yeah, it turned out pretty great. Not absolutely perfect, but definitely good enough. Now I'm just going to filter the whole bath back into the containers. I'm using a fleece filter here. I don't know, maybe 5 microns? So, these are all prepped and ready for a nickel strike. Remember, nickel is not something to mess around with, but it goes super fast and I'm wearing full PPE. I'm running a nickel anode, setting the PSU to constant voltage and aiming for a specific current target. Barely a minute later, we have a solid, flawless nickel finish. Here's the final breakdown of the 3 methods. Raw FDM, kind of a cool wipe, but it completely exposes every single layer line. Vapor Smooth, you guys kept bringing this up. I had my doubts, but it actually did a great job. Resin Print, the easiest to plate by far and gave us the absolute best finish. Now it's time to mount these on the doors around the house and see if the family can actually survive opening them. Honestly, it's a fantastic alternative to your boring standard handles, completely risk-free, obviously. Thanks for hanging out. The next video is dropping sooner, I promise. Tschüss.